though, those runoffs. You get more good stuff today. Okay, parametric equations. There is a mode in your calculator. We kind of troubleshooted, but I also said it's more important to get the basics, just to get an idea of what these types of equations are. First of all, these equations come in, parametric come in. Do you remember the word I kept using yesterday? Parametric functions or equations come in pairs, yeah. Parametric equations come in pairs. So you need two, an x equation and a y equation. Both of them have either t's or thetas. We talked about how you plug in points and you find a path, but didn't we, towards the end of class, say sometimes those paths can be hard? Especially this guy. Come on, check out his equation. Who is that guy? I don't know. But how did we figure out at the end of the day, after a little bit of math, that he was really just a downwards facing parabola? We said, let's ignore, and what's the snazzy term for ignore? Not just ignore, but take out. Let's not just ignore, but eliminate, take out t. Say, okay, you're so confusing in my brain because I'm not used to thinking in t's or thinking in time. I'm used just to thinking in the where or the x's and the y's. So to eliminate the parameters, some of them are easy, like the first example we did yesterday, where you take the x part, get t by itself. If worse comes to worse, we could take the y part and get t by itself and then go plug in. But usually we do whatever's easiest. You take the x part, but if possible the x, and then we plugged in and said, yay, t's gone, and I kind of know who you are. This one was a little bit harder, but we did the same thing. We took the x one, we somehow got t alone, and then we said, let's go plug in, and it took some work. We had to simplify what? A complex fraction? Took a little bit of work, but eventually we're like, oh, that's so much nicer. At least I know what the path is. We lost everything to do with the timing, but at least we know the path. But at the very end of yesterday was this guy. And the idea was, what do we do? And let me zoom in on this page just to make sure. I did it fast. What do we do when thetas come about? Now, I'd already warned you that thetas could come about. We could go to our graphing calculator, cool kids, and we could go ahead. I have to get back into parametric mode because I went out of it yesterday for calculus, and I went out of it again today for honors. But we can go back into par mode. Par mode. Parametric equations. I need two equations. Even though this guy has a theta, it's not a big deal. I can just say, well, okay, my calculator can't do theta in this mode, but it can do t. No big deal. No big deal. Just because they call it a theta, I can call it a t. I can do the 2 cosine t, and then I have 3 sine t. Some of you, your calculators were being kind of funny yesterday, so here's a chance to see if we got it all worked out, to see if it looks nice now. The 2 cosine t, the 3 sine t. If we graph, whoops, maybe zoom standard just to get a better idea. Does this look like anything? Oh. It kind of looks like it. I think I have a smudge on my calculator, or like a little, I have like a little mark. Yeah, kind of looks like it has little ears like a cat, and it kind of looks like it has little eyes and like a whoop. But no, it's just a circle, I think. I could zoom in. Isn't it an actual circle? Wait. This one goes over 2, and that one goes up 3. Wait. That one has a 2, and that one has a 3. Yeah, it's an ellipse. Wait a minute. Do you guys remember in that apps menu, there's that conic-y app, right? Isn't there a conics app?
Yeah.
Can't I go to conics? And do you guys remember that some of you, and maybe not all of you, but some of you were in a different mode, and I had you get back to function? Hit mode in that app. Do you see how there's func and par and pull?
Yeah.
Let's go to par mode. So wait, where am I real quick? I hear some of you just now joining us. So apps, boop. If I escape, sorry, escape. I don't want the info. Quit. Okay, I'm in the apps, right? Then where did I go? Conics section, because we just saw that this was an ellipse, and then there was an ellipse option in this conics menu. I went to mode. I changed from function mode to parametric mode, and if you guys notice, do you see A cosine theta? Maybe with a plus h, and B sine theta? Well, they don't put thetas, they put t's, because parametric mode has t's. But doesn't that look a lot like what I have? So one way is just to memorize brand new equations for all the conic sections. If you're like, wait, there are others? Yeah, we can go to hyperbola and see what those little conic, secant and tangent. We can go to parabola and see what those ones look. Oh, that's just with squares and weird stuff. Okay. Circles, what that one looks like. Oh, yep, sines and cosines. We could memorize whole new conic section formulas, but some of you are like, I don't even have the other ones memorized yet. Well, that's a dilemma. But there is another way, and the other way is, well, my hint from yesterday is if you get trig in parametric equations, try to find a property that relates the trig that you have. So when I saw cosine and sine, I said, ha, sine squared plus cosine squared is 1. Because sine doesn't equal something with cosine. Secant does. Secant equals 1 over cosine. Sine doesn't equal anything with cosine. Tangent does. Tangent equals sine over cosine, but that would make it all worse. This one makes it better because cosine squared plus sine squared is 1. I can get cosine alone with a quick division. I can get sine alone with a quick division. And then I can say, cosine, who are you? Oh, yay. I need to square you in this formula. Sine, who are you? That's a y. Yay, I need to square you in this formula. And guys, what does this look like now? Isn't that an x squared over 4 plus y squared over 9? Isn't this obviously, should be obviously, an ellipse with a major radius of 2 and a minor radius, nope, a major radius of 3 and a minor radius of 2. So how do you eliminate the parameter with trig? Solve for the trig. Go back and pull out a property from a long time ago. Plug in those expressions for the trig functions, and all of a sudden you have an equation. Now maybe y isn't by itself, but it's still an equation that we should know some stuff about.
How did you get the ellipsis formulas with
in here, hit the mode button right now. And when you hit the mode button in that little app, you can go from font to font. Or when we get to section 10. I didn't write it up yet. I started to. 10.7. If some of you want to, since you're already in your calculator, change it one more time because section 10.7, the last section we're covering in chapter 10, is polar. And isn't that the other option that you guys see right there? P-O-L? So you can already take a peek ahead and say, I wonder what the polar guys look like, because they're going to be even a little bit different. But we need to check homework first, or at least go over places you got stuck in homework. Oh, no, I already changed this, didn't I? Was homework last night 64?
Yeah.
Oh, okay. I put Friday thinking today was Wednesday, giving you guys 2 days. But today's Thursday, so if I give you 2 days for homework, like we said yesterday, this homework will be due on Monday. We'll go over homework questions first thing Monday before our little baby 10-point quiz on chapter 10B. Were you laughing at the baby part? Actually, I think honors Precalc, their homework's due Monday also. Not that you guys need to know that. Okay, so section 12.6. I think that's the end of notes. 10.6. I'm sorry. I'm still in chapter 12. It's limits. It's the beginning of calculus. I'm kind of invested in calculus, so I'm kind of distracted. I think, there was one more page. Oh, guys. Hardest stuff from section 10.6 we didn't get to do yesterday. It's pretty brutal. You ready?
Yep.
All right, pretty brutal. Before we have my sarcasm, the rest of you guys are they have to tell you what to make tea. If they tell you what to make tea, how do I get parametric if they give me function? How do I go the other way if they tell me what the path looks like, but then they bring in this whole timing thing? Substitute. Oh, really? Yeah. So y is equal to what if you go plugging in for a? Wait a minute, parametric come in pairs. So if y is equal to 1 minus t squared, don't I need x?
X equals t.
Oh, I can just steal it. Oh. But wait, letter B. Oh, it's going to get so much worse. Y is equal to?
Y minus x equals 1 squared minus x squared. Like 1 minus x squared.
y does equal 1 minus x squared.
Yeah.
But I need to plug in, don't I?
Yeah.
But I need x. That one was easy. This one's, well, how do I make it easy? Can't I add the x and subtract and get 1 minus t for x? Now can't I plug that in? Oh, parametric come in pairs. Oh, that's okay. I had to get x alone to even do the plugging in, so who is x? Huh. Now, could you simplify it and make it look prettier by foiling? I'm coming, Joe. Hold on. Could you make it look prettier by foiling? Yeah, you could. You could go ahead and do this whole 1 minus t squared. If I foil it, would be 1 minus 2t plus t squared. But I have a minus on the outside, so 1 minus 1 is 0. Minus negative 2t is positive 2t. Minus t squared is negative t squared. We could make it look prettier and simpler, I guess, more succinct, but yeah. All we have to do for these ones are basically solve for x. It's a little bit backwards of the other ones. Solve for x, then plug into the y equals f of x equation. Because if I solve for x and plug in, like this one, I'll get y with t's, and then we just have to remember that parametric come in pairs. So we'll have our y after we plug and chug, but we'll have to go back and get our x from our clue. But this x was quite easy. This x, I just had to rearrange, but I had to do that anyway to plug in. It's not too bad going that direction. Eliminating the parameter is a bit harder. I don't like old fashioned. What is that there for? Yeah, some of those chocolate ones were like stuffed and they had the stuff on the outside. Okay, now we're done. Section 10.6, let's grade. Maybe some of you are totally ready to grade. Maybe some of you needed some of that stuff we did at the end to finish, so maybe you're going to have to grade with the video at home. Either way. Either way. That's why I make sure to try to record the grading so you can always go back if you need to. Let's grade it even. I think. Oh no, I don't have it right there. I thought I did. Okay, so I do have a few different questions ready just in case. I think I know what some of the tricky ones are. So I guess I need to open up the document for answers. Hold on. Recap. Homework. Chapter 10. Okay, section 10.6, parametric equations. Do you guys have any odds right away while we're waiting for that to come up? Do you have any odds you already know you have questions on? Any odds? 67. Okay, cool. Anything else besides 67? Oh, hey, I crossed out 97, right? Didn't I eliminate him? Like he wasn't on the Google Classroom? Okay. He wasn't on Google Classroom. Sorry, guys. Anything else? On the odds? Okay. Okay, let me have you ask it while I get to the homework. Go ahead.
So for a lot of the problems, like there were times when you could like simplify it, I think, but I left it in.
Oh, I see what you're saying. Would it be kind of?
I didn't go like all the way.
Like this one kind of maybe. Like you would have written it like that and not that.
Yeah, I left it like that. I didn't go with the experiences.
There's a general like math thinking towards because you want to. In homework you want to get it right, right? But then the test and quizzes kind of gauge whether or not you're getting it. Just think this way: on tests, are there long answers? And long answers theoretically that would have been totally fine. I don't care as long as it's right, unless I say something like. Fully simplified. If I say something like that, or if I say something like FOIL out and combine, I don't know. Then maybe you should have kept going based on the directions given, but otherwise, Lauren, that's great. But what other types of questions are there? Multiple choice. Multiple choice, there's one set right answer in one set form, which could be what you did, or it could be what the back of the book did. It's just helpful for you to be like, wait, mine is that one. Could you be able to answer the multiple choice part? In calculus, we say a lot, could you make it match? You might have a correct version, but can you make it match with another correct version just written differently? Oh, I'll come back. What's up?
Like, I understand how to do it. I just get confused on making the table, like what numbers
Okay, number 14, let's peek at the question real fast. I don't think I have it specifically there. Did they give you any clue as far as the T's, as far as the low and the high? Sometimes they do, and sometimes they don't. So I'm going to peek real fast. But you can look at your directions also. The question is, do they give you any clues? In number 14, they totally don't. It's way down here, sorry. But there's no like T ranges as far as how low, how high. And up here, they don't give you anything as far as how low, how high. So my advice yesterday, if they didn't give you clues, was just to start at -2 like you would have in Algebra 1.
But so you start -2 for all of them?
If they don't give you any clues as far as the T's. Now let me show you where they do give you clues. So -2, -1, 0, 1, 2, a little bit negative, a little bit positive, 0 in between. This is a very Algebra 1-ish way of like, I don't know who to use. But what if they gave you intervals or clues like did they not at all? Yeah, don't worry, we talked about that yesterday. We can talk about it here too. Maybe they didn't. In calculus, they tend to give you ones with like where to begin, where to end. I think they're trying to make it easier on you guys to not make you change what's going on. Let me see if there's anything around here in the word problems, which I had you guys skip the word problems. So that wouldn't have helped you super well. I guess not. Anything? No. So Priscilla, the nice thing is with homework, you could have just used my clue yesterday of not knowing when to begin, when to end, so just starting at -2 every time. Except, yesterday when we were going through notes, I also kind of pointed out that parametric equations don't only have T's, they could also have thetas, right? They don't only have T's, they could also have thetas. And so I mentioned with T's, it's not a big deal if it just has T's, so just go -2, -1, 0, 1, 2, like I set up in the notes. But then I did, for this one, it actually showed like -2 to 3, which is why I went a little bit further. I went all the way to the end. And actually, to be honest, I should have cut this off at the last point because this says, here's the beginning. Here's the end, no more. So I should have actually stopped and said, okay, the thing started here, ended there, and here's the direction of the movement. So when it gave me a beginning, ending, I show that in my table. But right on this page, I did give a warning, but it was verbally. It wasn't actually me writing it down. I came back and I said, now, hold on, remember, functions can have T's and thetas. And so I gave a quick verbal hint that some of you might have missed, that if there are thetas, you're not going to want to use -2, -1, 0, 1, 2, because those aren't good angles to plug in. What have we been given since chapter 654? Unit circle angles. So in a table, you're not going to, for thetas, please don't put that in, that's gross. You have to go to your calculator, but pi over 6, pi over 4, pi over 3 would be a lot better. So let's go ahead and get back to our homework, but if we have a theta, Lauren, just stop me and we can peek at a theta as to what a table would look like. Priscilla, there's one that the -2, -1, 1, 2, sorry, 0, 1, 2 didn't work, just let me know. 23? Yeah. Okay. So getting up to number 23, first of all, we had number 14. We'll get to number 23. Number 14, if you were just to start with these basic values, you should have gotten your parabola, and then don't forget, check it. Did you put orientation arrows to say, hey, as I connected, it went this way? Because in a different problem, it might go the other way. Show the orientation. Huh? Time moves only in one direction. So I go from this point to that point to that point, the same way that time has to move. And so I say, okay, well, if he was at -5, 4, and now he's at -4, 1, well, then he must be going this way. Otherwise, the points would have been graphed in the opposite order. And then letter B had you eliminating the parameter, but if you guys solved that one, he was a lot like the example in the notes. Hopefully that was pretty straightforward. Y equals x squared plus 6x plus 9, or x plus 3 squared. Number 28, Lauren, if you don't mind, is really similar to 23 in that there are thetas. Yeah? So with the thetas, I mean, you guys can see what they did. They went ahead and just did 0, 90, 180, 270, 360. But if you guys didn't have a lot of experience, which you don't, with parametric equations, you might have just done all your unit circle. You might have been like, well, she said pi over 6, pi over 4, pi over 3. And if you had done that, it wouldn't have been bad. But let me show you why they didn't, because it's actually going to help us in the next section that we're going to today as well. Because in the next section, you're actually going to have to plug in thetas also and be a little strategic about it. But first of all, can someone give me a quick decimal equivalent? Because you guys have your calculators out to root 2. Can someone else give me a decimal equivalent for root 3? For root 2, it's 1.4-ish. And then for root 3, it's 1.7-ish. For Mrs. Leon, would probably know that to so many decimals of accuracy. But anyway. Yeah, she's a little human calculator. Why am I putting root 3 and root 2 right above a table with thetas that I'm going to plug in? If you were to do like pi over 6 and pi over 4 and pi over 3 before the pi over 2, and you would have had to plug into cosines and sines. I mean, 0 was a nice one. 0 is nice numbers of 7, negative 6. It's really easy to graph on my coordinate system. But as soon as we go to pi over 6, cheater chart, right? Isn't sine 1, 2, 3? So sine, this guy, the y is 1, 2, 3. So at pi over 6, he's 1/2, which would be 2. Minus 6 would be negative 4. That one's not bad. But if I go plugging pi over 6 into this guy, he's not 1, 2, 3. He's 3, 2, 1. He's root 3 over 2. Oh. 2 plus 5 root 3 over... Do you want to graph that guy?
No.
Most people say no. Now, if you know that root 3 is approximately 1.7, could you do 1.7 divided by 2 is approximately 0.8 times 5 is approximately 4, and 4 plus 2 is approximately 6? I mean, yes. But if you could avoid it, wouldn't it be nicer to avoid the nasty radical thing?
Yeah.
And then if you went to pi over 4, I mean, that's pretty bad because both of them are root 2 over 2s. And so both of them are going to get nasty things as far as like 2 plus 5 root 2 over 2, whereas this one's going to do negative 6 plus 4 root 2. And yes, you could bring in the 1.4 and approximate, but and pi over 3 is going to be, well, he'll be nice. 3, 2, 1. He'll be nice for cosine because cosine is 1/2. 2 plus 5/2 or 2 plus 2.5 is 4.5. I don't mind cosine for pi over 3, but sine's going to be gross. It's negative 6 plus 4. No, that would reduce with a 2. 2 root 3. When we plug in thetas to expressions, sometimes we're going to jump to only the guys that we like, hoping that it's enough information. Sometimes it is, and sometimes it's not. Sometimes it's not. You guys help Priscilla out. Sometimes it is, and sometimes it's not. Now, do you guys see that zeros and 90s are pretty nice for cosine or sine? They're pretty nice for cosine or sine. They're 0 or 1 when you plug in. Pi over 6s, this is going to be helpful for section 10.7. Pi over 6s are nice for sines. Pi over 6s are nice for sines. Sine is equal to 1/2, and I can do that in my head pretty easily. No root 2 over 2, no root 3 over 2. Pi over 4 is basically not nice for anybody. And pi over 3s, yeah, who are they nice for? We're going to use that in section 10.7 just a little bit, so just a heads up. If you're having to choose angle values to put in the table, if you only have sines, you can throw in pi over 6s. So 0s, 30s, 90s, 150s, 180s. You can throw in like the normal ones like they did here. But then you can also throw in pi over 6s. If you only have cosines, you can throw in pi over 3s instead. But if you have both, like this example, they said, forget it. I hope this is enough. And technically, guys, if you graphed all of your points, 7, negative 6 was here-ish. 2, negative 2 was here-ish. Negative 3, negative 6 was here-ish. 7, negative 6, sorry, 2, negative 10 was here-ish. That was more than enough information to be like, hey, there he is. So why did they choose these guys? Because they were nice. would you plug in though, Kate?
Because I didn't know what to do
Right.
for this one, so I went to 23 on CalChat and I just plugged in the same ones. But then mine are out of order, so I'm not sure.
As in, like,
How did mine circle?
like, what numbers did you, because when you plug in angles, you need to plug in, like, in order of going around a circle. Otherwise, it's going to chuck around.
Well, that's what I did. I did the same as the ones for 23.
Okay, and what were the angles for 23?
0, 5,
Oh, nice. So the nice thing is you ended up plugging in the exact same ones, right?
but then I didn't see this way.
These are mixed up?
Yeah.
Okay, then it must have been when you were plugging in your unit circle, got a little switched around. So maybe you were plugging in zeros and it should have been ones and ones.
Yeah,
Just be careful with your unit circle. That's what would have got
If this is on a test, would you want us to do like pi versus pi,
Well, remember how I was saying that these make everything nasty, so this is why they chose these ones? So I'm okay with you choosing these ones. The problem is though, in a more complicated graph, especially in the next section, you're gonna miss like gaps in between and not know exactly how it connects. So that's why I was giving you just a little heads up that we don't mind bringing this guy in, but only for sines. So since this guy is both sines and cosines, I would have left all of these out, just like the book did. I was just trying to show you, hey, but he's not bad if he just has a sign, just for future reference. And I'm like, and he's not bad if you just have a cosine, just for future reference.
but then how do you find out the whole circle is hitting this too?
Oh, well, we had all these points.
Well, but like I mean, if we did the other way.
Oh, well, if you did the other way, you would have had all these little decimal things also. Like if you had gotten decimals, you would have had all of these. So it would have been a prettier connected dots. But still would have been the exact same graph. You just would have had tons more points. And you would have had little decimal ones of like, -4 was your y. At -4, you have this. 5 times 1.7 would be 8.5 over 2, so 4.25, 6.25. Like you would have just had all these nasty decimals that you would have been. Okay. Whew, let's finish grading homework real fast. Eliminating the parameter, hopefully you guys see that you would have gotten cosine alone and then thrown him in the cosine squared property. You would have gotten sine alone and then thrown him in the sine squared. And you would have gotten your ellipse. This guy has an h and a k, so to get cosine alone you would have had to subtract and then divide, but that gets put in. And then add and divide, that gets put in. For number 44, it was just like, hey, how you doing with your calculator? And it was the first time, and well, except we saw it today when we were in this mode that I had you guys do. But if you did this last night, it would have been the first time that you saw, wait a minute, a secant and a tangent makes a hyperbola? Anyway, yes, a secant and a tangent makes a hyperbola. And then number 58 said, okay, wait a minute, if you just figured out that there's a way to make an ellipse from equations, which technically you were given way up here. They said, can you try to use those equations to get this ellipse? And so it was basically seeing if you could use this way of writing an ellipse in parametric equations and figuring out who's my h, who's my k, like from chapter 10a. What's the halfway point? 3, 3. That's my h. Throw them in. That's my k. Throw them in. Then you could have figured out from your foci who your C was. The distance is 4, who your A is, thrown into your formula. So it had you do like a section 10A problem, but ending in parametric instead of ending in standard form. Ending in parametric instead of ending in standard form. Lauren, are you asking about 58? So the cool thing is technically you didn't even have to go straight to parametric. You could have just said, oh, I know this thing about ellipses. That is x minus over, and then y minus, all over. And just like I showed you last chapter, the test that you just took, you could have graphed 1, 2, 3 with 7. And then 1, 2, 3 with -1. You could have found the halfway point to be 3, 3. And you're like, oh, hey, cool. My HK at my center 3, 3. You could have graphed your foci. Well, actually, right here, you could have figured out the distance is 4. So that's why A is 4. And A is vertical, which would put the 4 there. They tell you about the foci being at 3, 5. And so if you would have graphed that guy, you're like, oh, hey, that's only 2 away. So C equals 2. You would have taken that equation from last chapter, that C squared is A squared minus B squared. You would have plugged in 4 equals 16. B squared actually ends up being 12. So I don't even have to plug in B squared. I can just plug in, I should say, I don't have to plug in B. Then my center is 3, 3. And you can take this standard form from last chapter and go put it in parametric. In parametric, as we just saw on the calculator, and like you had seen earlier in homework, you just need to put the H in that spot, the K in that spot, and up there. The A, so square root of 16 is 4. And then the B, square root of 12. Well, square root of 12 can be rewritten. Once again, if you can make it match on a test, that would be best, right? So 12 is 4 and 3, square root of 4 is 2. So basically it was getting the standard form and then saying, but there's a parametric way. And what did I just show you guys on your calculators that you will be allowed to use on the quiz on Monday? You can go mode, you can go par, and you can go ahead and look at any of these guys that you might need as far as where to put your H's, your K's, your A's, your B's, right? Okay. We need to at least start 10-7. I know I'm only doing the short, sweet version of it. But since we need to start 10-7, I think I have 67. Oh, I have 97. Here, let's just change it to 67. Because one of you guys had a question on that. We can peek at him fast, but I need your notes open and ready to go, okay? So number 67, who is he? He was what we just did a second ago in the sense of getting parametric equations from a rectangular equation. So you probably had a question on this because we didn't get to do it yesterday as an example. We ended up kind of going over that one in notes. Let me get rid of that. But 67 gives us a little bit different clues. In that it says, and it was important to read the directions as it always is, it said, hey, t equals x is going to be your first guy, and t equals 2 minus x is going to be your second guy. And so as we saw a moment ago, these aren't as bad as they seem. They just feel kind of yucky because you didn't get as many examples, especially yesterday. But it was super important to take that and to take this and to realize they wanted us to go from function to parametric. So from function to parametric. Well, you know parametric come in pairs. So we're going to need an x guy and a y guy for A. And for number 67, again, we're going to need an x guy and a y guy for B. But the nice thing is they gave us clues. So guys, for A, who's x equal to? And since x equals t, can't I plug it in the x spot? Yep. So y is t squared plus 1. Probably easier than you realize. You just hadn't seen it when you did homework last night. But what's a little different in B? Because I still have to have x.
Not t anymore.
Yeah. So it's up to you guys. You could have, maybe some of you would have subtracted the 2 first. But how do we get x alone?
Switch it.
Switch it. You could add that and subtract that, or you could multiply both sides by a. Flip all the signs, right? So then x is equal to negative t plus 2. Or you could have done 2 minus t. In my head, it's a little bit easier, but either way. So you have x. As soon as you have x, you go plug it in. As long as you don't kill a puppy, you can make that look nicer. But that's technically a correct representation of the parametric. If you guys need a picture of that, go ahead and grab it. That was number 67. Once again, sorry for not getting that example to you guys yesterday. I bet that's the main reason as to why we had that question. Bloop, 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 bloop. It is time to change your calculators to Get out of the ellipsy dude, of the conic sectiony dude, but mode. Oops, you can't see it. Go down to function and say it's time for polar. I want you guys to change to polar and then go to your y equals and be like, ooh, that's different. That's different. R's? Betas?
R's.
No wonder I talked about betas today.
It's just R's.
It's just R's. And some of you are seeing the graph on the screen and you're starting to freak out a little bit. Hang in there, you're okay. Parametric was weird because you had to take a t, plug in a t, to get to x, y, to go to the graph. The t didn't go in the graph though. Parametric was weird because you had to start with a t and he didn't end up on the graph at all. He just told us who we were allowed to graph. We needed x's and y's for graphs. 10.7 is going to be weird because, well, we're not putting x's and y's on the graph at all because we don't have x's and y's. What do we have instead? R's and b's. And 7 is going to be weird because you don't have x's and y's, you have r's and betas. Now, the x's and y's are still kind of there, hidden in the background. I don't know, this is really light, huh, guys? I don't know, I feel like the projection is weird today. Yeah, I'll zoom in. I wanted you guys to see this graph, but let me zoom in. We don't actually need that big circle-y thing. The x's and y's could still be shown. I'm going to put them on there just because technically they're kind of hidden behind every polar graph. Just they're a way harder way to get there. Sorry, I'm covering up right now directed angle, the angle of the direction. R is the directed distance. We could still technically have an x and have a y. We could still technically. We could even technically say there kind of is an x-axis and kind of is a y-axis. But if you guys can tell, this graph is way different. And if you were to do something like Google graph papers or Google like graphing grids, you would come up with a good old-fashioned XY graphing grid. You would, but you would also see things like this one, the polar grid. Check on your group real quick. Make sure everybody has these notes down. If not, give them a high five, give them a shake on the shoulder in the back. Check on it. Here we go. Section 10.7. What is what equal to? I don't see it equal. That's a colon. So the colon is for me to talk about who this is. That's a colon. Oh, way up here.
Yeah.
P equals R comma theta. This is theta. Is the directed angle. This is 0.0 for, I don't know, they call it 0.0. This is the polar axis. This is a colon because I need to tell you who R is. R is going to be our radius, is one way of thinking about it. Over here it says directed distance, and this is going to be our direction angle. You can say directed angle. I like direction angle better, but either way. And polar graphing is all done on what we call a polar grid. So a couple things about a polar grid. You guys do not have to draw the whole thing, but I just want to make sure you have the idea of it. Okay. The polar grid has what we would, well, what we used to call the origin. But now we call it the pole. What we used to call the origin, but now we call it the pole. It has a 0 angle line, which is our standard position beginning. It's still going to be our beginning for all the rotations that we're going to do, because we're going to have to rotate this theta. And that's going to be called And you see it up above, the polar axis. It used to be called the positive x-axis. Now we can call it the polar axis. But we can also call it the theta equals 0 line. We can technically also call it the theta equals 180 line, or the theta equals pi line. We're going to identify stuff in this graph not by x's and y's, but by thetas. Yeah. Well, I'm starting to show you the important pieces, and I figure that as you need to, you can kind of start building it. So right now we've drawn an origin. We've drawn out a positive x-axis, calling it the polar axis, or the theta equals 0 line. This one used to be called the positive y-axis. Now it's technically called the theta equals 90, or you could do the theta equals pi over 2 line. And then I want you guys to see that technically, even though it's not very clearly shown, it's not really shown at all, you can still think of there as being tick marks on what was the x-axis is now the polar axis. And you can still kind of think of there being tick marks on what was the y-axis, but is now the theta equals 90 degree lines. Yeah. And some of you might be like, why on earth are we doing this? Why is that called the pole? Where do penguins live?
North Pole goes around the pole.
North Pole, South Pole. Couldn't this be looking down on the globe?
Yeah.
Couldn't these be the radial lines? Radial lines, oh, that's nasty. Couldn't the radial lines be longitudes?
Yeah.
And couldn't the angle lines be latitudes?
Yeah.
So maybe this is a coordinate system on a sphere as opposed to a coordinate system on something flat. So let me walk through what these are. Now if you guys notice, do you see how the tick marks, the one tick marks kind of, it's like I have a compass and I'm rotating the compass. The ones, the twos, the threes, the fours, do you see how we can connect them and it kind of forms our graph? The ones, the twos, the threes, the fours, we can actually call all of these radial lines. Why are they called radial lines? Can you think about them as being formed from radiuses?
Like circle.
Yeah. Radiuses, that's awkward. How about radii? Can you just go radii instead? But I wanted you guys to see the word radius. So radial lines can be formed by the radii. Because if you guys notice, these are just concentric circles. This guy would have a radius of 1 tick mark out every direction. I could keep him going if I wanted. This guy would have a radius of 1, 2, because I went out 2 tick marks, and I could keep him going all the way around. And I'm not going to make you do the whole graph, but you see the pieces. I have this polar axis guy. I have these angle lines that can actually be for every single 15, 30, 45, 60, 75. They can be in degrees. They can be in radians. I have these radial lines. These guys are going to be my angles, my angle lines, or my theta lines. How do we put all this together? Let me just show you a couple points real quick. What if I was to have you graph the point A and graph the point B? For the point A, I'm going to have you graph, let's just do 3 45 degrees. This is how a point's going to look. And 3 denotes a radius, and 45 denotes an angle. So couldn't I go to the 45 angle line, guys? And couldn't I go out 1 radii, 2 radii, 3 radii?
Yeah.
So where would the third radial line and the 45 line connect? Right there. Pause, let me show you one more weird thing. What would negative 3, 45 be? You still go on the 45 line, but instead of going 3 in a positive, I like this person, I'm moving towards them way. I'm going to go in the negative, nope, I'm headed the absolute opposite direction. Alright, let's see later. Polar, point. These are mine. Go be inspired by polar bears. Polar bears!
Polar bear.
Polar bears, polar points, polar graphs, polar name. Bye guys.
They don't have white for me. I have a side that has
Today, right?
yeah.
But in
It's
the
like
afternoon?
12.